this will be the start of epsilon delta proofs. So say we have a function, a simple function, f of x equals to x plus 4. And we want to prove that the limit as x approaches 1 of f of x equals to 5. This might seem obvious to many of you, but we just have to prove it. And proving is harder than it seems. So we will use a type of proof called the epsilon delta proof to prove these limits. There are always two steps to these epsilon delta proofs. The first step is the pre-proof step. And we will divide our paper like so. And this side will be the actual proof. Okay? So in our pre-proof step, let's see what we want to show. We want to show that for any epsilon, we can have that f of x minus 5 is less than this epsilon. Okay? Right? So for any epsilon, we want to be able to have that absolute value of f of x minus 5 is less than epsilon. Now what's f of x? F of x is x plus 4, and then we can simplify this. So we have x minus 1 is less than epsilon. That's what we want to be able to have. So this is what we need. We need this to be true in order to be able to find a delta. So let delta equal epsilon. Then if we have 0 is less than x minus 1 is less than delta, right? This is given by the limit definition. Then we'll have 0 is less than x minus 1 is less than epsilon. And we can go backwards to x plus 4 minus 5 is less than epsilon. And 0 is less than f of x minus 5 is less than epsilon. And basically this statement proves that for any epsilon, we can set the delta to epsilon, and then this delta will force this delta that we chose to be epsilon, will force f of x minus 5 to be less than epsilon. We could have chosen epsilon equals to, delta equals to epsilon over 2, or delta equals to epsilon minus 1. Either way, we just want to show that we can find a delta based off of any epsilon such that f of x minus 5, the absolute value, is less than epsilon. So now that we've shown this, we have directly proven that the limit as x approaches 1 of f of x equals to 5. Example 2, this will be a little bit harder of a epsilon delta proof. So say our f of x equals to x squared plus 2x minus 1. Okay, and that we want to show that the limit as x approaches 3 of f of x equals to, well, we're expecting that the limit as x approaches 3 would equal to f of 3. So let's see, 3 squared is 9, 9 plus 6 is 15, minus 1 is 14. So we hope that this equals to 14. Okay. Now we have our pre-proof and our proof. So the purpose of the pre-proof is to find the is to express x in terms of epsilon, because we already know that x minus c is less than delta. So if we can express x minus c in terms of epsilon, then we can relate these two and we can show that we can always find a delta. So that is our goal in our pre-proof step. So for this example, let's write it out. We want to show that x squared plus 2x minus 1 minus 14 will be less than epsilon. Okay. Now this can become x squared plus 2x minus 15 is less than epsilon, and we can factor this. So factoring, we get x plus 5 times x minus 3 is less than x epsilon. Okay. Now we can split these absolute values here. So we get absolute value of x plus 5 times the absolute value of x minus 3 is less than epsilon. So now we see we have our x minus 3, which looks awfully familiar because we have our limit going as x approaches 3. But we have this pesky x plus 5 term here. And here is the big brain move for this proof. We can restrict our x. So x will be restricted between, say, an interval 2, 4. So note that this interval is like within 1 of 3. Okay. So by this, we will have that 7 times, because we're plugging into x plus 5, 7 times the absolute value of x minus 3. It will be strictly less than x plus 5 and x minus 3 absolute value, and this will also be strictly less than 9 times the value of x minus 3. Okay, and we see here by the transitive property 7 times x minus 3 is less than epsilon, and therefore x minus 3 is less than epsilon over 7. So back to our pre-proof, back to our proof now. We can let delta equal the min of epsilon over 7 and 1. So basically, if we have any epsilon given to us, if epsilon is really big, like epsilon will be 100, 1 will be the minimum. And clearly if epsilon is really big, delta of 1 will be pretty small compared to it, and the values around c will be only 1 less or 1 more, and those will clearly be in our interval of epsilon. However, if epsilon becomes really small, epsilon equals to 1, then our delta will be epsilon over 7. We can do this because we can choose our delta. The power in these proofs is that delta is up to us to choose. We just need to find how it relates and how to pick it relative to epsilon. So now that we have our delta given, we can be saying that x minus 3 will be less than epsilon over 7, and x plus 5 is less than 9. So from here we have that 7 times x minus 3 is less than epsilon over 7. But now we see that we have a 7 here. And we want to turn this back into an x minus 5. Remember, we wanted to show this. So we want somehow this to become x minus 5. It seems like we're a little bit stuck here. Because this would only mean that x would have to be x plus 5. Sorry, that's what threw me off. This has to be, we want this to be x plus 5. However, x plus 5 can be between 7 and 9 if we let our delta be minimum of 1. So what we want is this to actually be a 9. We want this to be a 9 here.